Want to talk about intensity and sound intensity level in this video. Let's just get right to it. Intensity is power over area. If you drink a lot of beer, you can remember it as drinking IPAs. So I try to use this script P for power just to tell the difference between, say, momentum or pressure or density, etc. Intensity also happens to relate to S max. That was the displacement amplitude. So remember, the molecules in a sound wave are wiggling back and forth, but on average, they stay in the same place. So if you know the displacement amplitude, you can figure out the intensity or vice versa. It depends on frequency, density, and speed of sound. There we go. V sound looked kind of weird there. Sound intensity level. In short, this is just your decibels. Okay. The real unit is a bell, and then a decibel is 10 to the minus 1 bell. So, but we always use dBs. So a lot of people will say dBs. I say dBs. Sound intensity level, decibels, dBs, beta, all of those are kind of interchangeable. Notice it's based off a logarithm, and that's log base 10. You're going to hear me call this log, and I'm just going to expect you to know I mean log base 10 when we're talking about decibels. Just like when I say log, and I usually mean natural log. And I apologize for this. I'm just being straight with you. A lot of people do this. They just say log and expect you to know whether it's log base 10 or natural log. The default is usually natural log, so I guess the exception would be you might actually emphasize log base 10 for these problems. And almost all the other logarithms in physics are natural logs. So maybe I'll try to say log base 10. All right, anyways, so here's the unit sitting out front, log base 10 of this, where I0 is your reference frequency. And reference intensity. I guess maybe I should have mentioned this before, but notice the units of intensity are watts per meter. Power has what unit? Watt unit over area, which is meter squared. So that's where we're getting those units from. All right, enough on that. Let's get straight to an example here. So now I want to imagine, oh, you can tell we're going to have a ball with this problem, huh? So imagine you have a speaker. Pretend this baseball is the speaker, and it's emitting sound isotropically. Oh my gosh, this is all these big words. And then I want you to find intensity and beta 30 centimeters from the source. Assume attenuation is negligible. Well, first let's explain what this means. Isotropically, that means same in all directions for this problem. So this is just a fancy way of saying it emits the sound spherically. All right. So just in case some of those words pop up in your homework assignments, now you'll know what they mean. All right. Emits sound isotropically, emits sound the same in all directions, emits sound spherically. For this type of problem, that's all the same thing. And I guess I should have said determine. All right. And now attenuation. Just think of this as like absorption. Absorption. Hopefully I'm spelling that right. I don't know. Anyways, when sound waves travel through the air, there's going to be some absorption of that energy by the molecules. It won't all get transmitted. We're going to ignore that. There's some problems in the workbook where I include attenuation, but to be honest, I don't plan on doing too much with attenuation on tests in my Physics 162 class. Your instructor for your class might be different. But so I'm just mentioning it in case you read that or wonder what attenuation means. All right, so basically for my classes, I'm probably just going to ignore attenuation all the time. You wouldn't have to know. All right, so let's figure this out. Intensity, IPA. Okay, so let's think about this. it's emitting the sound. Oh, well, I guess that's why I got these stupid beach balls out, right? The sound emits spherically, so it's heading out all over the place. And this thing right here, this is a 60 centimeter ruler. So you can see that's about the right size of this ball here. So what I'm saying is the sound is emitted here. Imagine this baseball is right in the middle of this beach ball. And in that case, what is the intensity at the surface of this beach ball? So what is the area I should use? Think, is it pi r squared? No. The area is the area over which the sound wave has spread out. It's the surface area of a sphere. 4 pi r squared. If you remember the volume of a sphere, 4/3 pi r, or 4/3 pi r cubed, you can take the derivative to get the surface area, 4 pi r squared. So we're going to say the power is, what was it? 555 milliwatts. The area is 4 pi. I'm going to convert this to meters because I know I want to get beta, and beta used a constant that had meters in it. Crank it out, race you. 555 e negative 3, divide by 4, divide by pi, divide by 0.3 squared. I got 0.4907. We'll keep the extra digit, but indicate where we're going to round. So now let's get beta. Oh, let's use a different color. Let's get beta. I'll race you. I over I0. I0 is 10 to the minus 12 watts per meter squared. This was the intensity at my location. Notice the units drop. This is why I was saying you want to use meters here so they cancel out. The argument of a log. I called it log. I said I would try to be better. You can see I'm not going to be. Log base 10 of blah, 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 blah. Okay, let's cancel out the units. All right. So divide that by, careful when you do this. You do not type 10 EE negative 12. It's 1 EE negative 12. Right? Because this is 1 times 10 to the minus 12, not 10 times 10 to the minus 12. No, bad, bad, no, bad. Okay, so now I got to take log base 10. Ugh, I just hate saying that. That answer. And then I have to multiply by 10. And we're going to go down. What is that, 116.9 dB? So in your book on page somewhere, I think at the bottom of page 47, I should have said this earlier, page 47, there's a chart. Oh man, that's like a jet. Dangerous for over 30 seconds. So maybe you shouldn't stick your ear right next to a speaker that's cranking out that much power. All right. Oh, I can still hear that slinky. The ball hit the slinky, whatever. Maybe you don't know what I'm talking about yet because that's in a future. I don't remember where we're at, whatever. All right, you'll see what I mean, foreshadowing. Okay, that's example 1. Let's get to example 2. This one is kind of tricky, all right? You have the sound emitting from the source, and let's take it one step further. A circular membrane of radius 20 millimeters. Can you think of any circular membranes of about that size? Your eardrum is about that size and shape. So imagine a tiny little membrane pressed up against there. So obviously, not all of the sound energy is going to go into my ear. Only some of it will, right? Only the part that's basically, imagine a small, obviously this is too big, but if you just pretend it's one of these dots, how much sound energy is incident upon one of these dots, but then make the dot a lot smaller. So hopefully, I don't know if you can see that, but yeah, the sound energy incident on one of these dots, but maybe much smaller, 2 millimeter, what was it, 20 millimeters? So a little bit smaller than one of those dots. And this should be a question mark, I suppose. All right. So now I'm talking about power. We know something about this speaker. How could we figure this out? I know that the intensity, IPA. But now I want to add some subscripts to this. Intensity at membrane will equal the power absorbed by membrane times the area of the membrane. If we go back and compare it to this one over here, this was intensity was the power of the source times this area, which it's a different problem. This one was talking about the intensity at 30 centimeters. I think, is that what it was? Yes. So notice in this case, the power absorbed is not the total power emitted. So you have these, I hope this makes sense. This is really where these problems get kind of annoying. You could talk about the intensity of sunlight emitted, the intensity of light emitted by the sun, or the intensity absorbed by a solar panel. They're different things, right? So not all of the power output of the sun goes into a single solar panel. This is the same idea, and this shows up in a bunch of different calculations. So even though they're easy, you do get this little bit of confusion as to which power are we talking about. Here I was talking about the source. Here I'm talking about the membrane. So once you get there, it's pretty easy. So I'll see power of the membrane is equal to I at the membrane times area of the membrane. Now, in this case, right, the intensity at the membrane, that was what we figured out. At 30 centimeters, where the membrane is located, that would be this number right here. So I'm just going to put it like this. Power of the source over 4 pi x squared, where x was the distance away, right? And then the area of the membrane, think, it's a circular membrane. That one is pi r squared. So in this case, x is your distance from the source. That's your 0.300 meters. And this one is your 20.0 times 10 to the minus 6. Was it 6? Oh, 3. Okay. So that's what's going on in here. And so if we calculate this, I'll go ahead and get the number. You can race me. What was it? This was that number times pi, oops, times pi times, what was this? 20 e negative 3 squared. What did you get? 0.006, 616 microwatts. Oh, that's going to run off the board, isn't it? That rounded correctly. Oh, it should be 617. Sorry about that. Something like that. So that's how much power is going into the actual membrane. All right, so I just want to, I know you can stop this video now, but just really focus. Pay close attention if you should use the source power or if you're looking for the power absorbed by something. They both use the equation IPA, but you have to think carefully about the area used. And when we're doing spherical emission, remember it's 4 pi r squared, not pi r squared. Those are the most common mistakes.